the remainder in the Taylor series. Suppose you have a Taylor polynomial that approaches the sine of x. Then, if you stop, say at x to the power 5 or x to the power 7, how good is then your approximation of the sine? Well, here, take this Taylor polynomial of degree 5, x minus x to the power 3 divided by 3 factorial plus x to the power 5 divided by 5 factorial. How good is it if you want to approximate the sine of x by this polynomial? Or if you take the polynomial of degree 9, how big is the remainder or the error that we will make? Suppose now we have a function f, and this function is at least n plus 1 times differentiable and has a Taylor polynomial in axis a given by the standard formula for p of x is equal to f of a plus the first derivative of f at a times x minus a up to the nth derivative of f at a divided by n factorial times x minus a to the power n. Then there is a c between x and a such that the error that we make if we approximate f of x with p of x, so f of x minus p of x, is equal to the n plus 1's derivative of f at this point c divided by n plus 1 factorial times x minus a to the power n plus 1. So here you see how big the error can be. Of course it depends on c, but the c we know something of, namely it's in between x and a. In particular, if our function f, the n plus 1's derivative of f, is bounded on an interval around a, then for x in that interval we do find that f of x minus p of x is at most a constant times x minus a to the power n plus 1. And that is what we call of order big O x to the power n plus 1. Namely, big O notation gives us a way to compute an upper bound for an error. We say f of x is big O of g for x going to a if there is a constant k and an open interval I around a, such that for all x in this interval we do have that the absolute value of f of x is at most this constant k times the absolute value of g of x. For example, the sine of x is big O of x when x is approaching 0, as sine of x is less or equal than x around 0. Of course, we should have here the absolute value of x. A second example is 3x squared minus x to the power 5 is big O x squared if x is going to 0. While why? Well, 3 times x squared minus x to the power 5 in absolute value is at most 3 times x squared plus the absolute value of x to the power 5. But if x is in the neighborhood of 0, then x to the power 5 is certainly less or equal than x squared. If you take x at most 1 from 0. So we get that the absolute value of 3x squared minus x to the power 5 will be at most 4 times the absolute value of x squared. And indeed, we find that 3x squared minus x to the power 5 is big O of x squared. We can use this big O notation to explain how the Taylor series approach some function. For example, e to the power x we can write as the first terms of the Taylor polynomial up to x to the power n divided by n factorial, and then the remainder will be big O of x to the power n plus 1. The sign of x we can also approach using the first part of the Taylor series up to the term with x to the power 2n plus 1, and then the remainder will be big O of x to the power 2n plus 3. That means that the error that we make is at most a constant k times x to the power 2n plus 3 in the neighborhood of 0. Similar approximations we do have for the cosine, the ln of 1 plus x, and 1 divided by 1 minus x. Here we show you how you can compute with this big O. We know that the sine of x is equal to x minus x cubed divided by 3 factorial, and so on. And that the sine of x is x minus x to the power 3 divided by 3 factorial plus big O of x to the power 5 for x approaching 0. Sine of x is also x plus big O x to the power 3 if x goes to 0. We just end the power series somewhat earlier. But how about the square of a function of which we know that it is x plus big O of x cubed? Well, you just take the square and then you find it's x squared plus big O x to the power 4. Why? Well, x plus big O x to the cube times x plus x plus big O of x to the power cube is of course x times x is x squared. X times something of big O x to the power 3 is of course big O x to the power 4. Same way, big O times x to the power 3 times x is also big O x to the power 4, and big O x to the power 3 times big O x to the power 3 will be something which is big O x to the power 6. But if something in the neighborhood of 0 is big O x to the power 4 plus big O x to the power 4 plus big O x to the power 4, then it's certainly also big O x to the power 4, just one single term. It's a constant, less or equal than a constant times x to the power 4, plus another constant times x to the power 4, plus a third constant times x to the power 6, but that we can bound by some big constant times x to the power 4. So we do have that it is x squared plus big O x to the power 4. In the same way, we can find that x squared plus big O x to the power 3 divided by x is equal to x plus big O x squared. You can think of big O as a kind of wastebasket in which you put all the things that you can neglect. But you just not throw away anything just at random. You just keep some control over its size.